In section 3.6, we're going to work on graphing so-called rational functions. So rational functions would be something where you have the ratio of two polynomials. So we'll call it r of x is p of x over q of x. So p of x and q of x are both polynomials, and you're going to divide those two. You're going to divide them and get some kind of a rational function. So a very simple example of a rational function is this one, y equals 1 over x. In fact, it's the simplest example of a rational function. You got really a constant, but you can call it a polynomial in the numerator and 1 in the denominator. It's about as simple as it gets. Now, before I graph this, let me put it into my calculator here, and you don't have to keep up. Let me just do it up here. Let's put in that function 1 divided by x, and let's go to the table feature and think about, plugging in certain values into 1 over x. Now let me plug in some values going far out the x-axis. So some really increasingly big numbers. So I'll start with 10. And if I put in a 10, I get 1/10. If I put in 100, I get 1/100th. And I think you can kind of see the pattern, 1,000th, 10,000th, etc. Now it starts to put it in scientific notation. This is 1 times 10 to the negative 4th. So that's 3 zeros and then a 1, and so on. 100,000, I get 5 zeros. Overall, what's happening to the y values as you move out the positive x-axis? What's happening to? You're getting closer and closer to 0. They're getting close to 0. Now, if you went in the other direction, a similar thing is going to happen. If you go out negative 10, negative 100, negative 1,000, etc. A similar thing is going to happen, except this time they're still approaching 0, but they're negative. Okay, so that's fine. Either direction you go out the x-axis away from x equals 0, the graph gets closer to 0. What if you're close to 0? Let's put in some values close to 0, like 0.1. Yeah, well, that's really 1 divided by 1/10. If you take the reciprocal, you get 10 over 1. 0.01, 0.001. So as you get closer to 0, what's happening? These values are getting really, really big. And if you kind of put those two observations together, you're going to get the graph of your function is going to look like this. So as you move out the x-axis, this graph gets closer and closer to the line y equals 0, or basically the x-axis. Because as you divide 1 by increasingly larger numbers, the quotient's going to get kind of small. Similarly, if you move out the x-axis in the negative direction, you're going to get a really, really small quotient. This time it's going to be negative. And last but not least, if you divide x by a really, really small number, getting close but not quite touching 0, that quotient's going to just take off. Now there's two behaviors that you should see here. One of them is this vertical line. That vertical line comes from the fact that we can't let x equal 0. But when we get close to 0, we have what's called a vertical asymptote. And that's one of several features of a graph that I'd want you to be able to find here, are the vertical asymptotes. So it's a line that the graph approaches. It'll never actually touch it or get there. In a similar manner, you've got a vertical asymptote here at x equals 0. There's another asymptote for this graph, and that is your horizontal asymptote. So if you move out the x-axis in either direction, this graph gets close to but never quite touches the horizontal line y equals 0. So this graph actually has two asymptotes. And our goal in this section is to graph these types of functions and to find those kinds of features of it, vertical and horizontal asymptotes. By the way, let's figure out the domain and range of this. What's the domain? This is good review for your test this Thursday. What's the domain here? Yeah. Basically, it's everything except 0. And if you just want to write x is not equal to 0, that's fine. It doesn't include x equals 0. How about the range? What are we going to get for the range? All real numbers except 0 again. This never quite touches the x-axis, so it gets close as you want, but it never touches the x-axis. So there's your domain and range. So let's take a look at some other functions. Now, the idea, at least with the early problems for me, is that we can try and figure out what these graphs look like simply by shifting them. So the graph of y equals 1 over x is something that I'd like you to know. But if we know what this graph looks like, maybe we can figure out what the graph of r of x equals 1 over x plus 4 is going to look like. How is that graph going to be shifted compared to the graph of y equals 1 over x? Yeah, to the left 4. You can think about what makes the denominator equal to 0. Instead of the denominator equals 0 when x equals 0, this denominator equals 0 when x is negative 4. So that represents a shift to the left by 4. In problem 14, they asked you to graph the function and state its domain and range. So its graph is simply going to be this moved to the left by 4. You can look at its domain in kind of an algebraic way. Algebraically, looking at the domain, we realize that x can't equal what number? Negative 4. X can't equal negative 4 because that would make a 0 in the denominator. But the range, if you just take this graph and shift it to the left by 4, the range is still going to be the same. Y is different than 0. And you can take the time to graph these on your graphing calculator or on Desmos if you happen to be at home or near a laptop. But my idea and my goal here for you is to try and figure out what these graphs look like without necessarily graphing them. So it's understanding some more about the shifts. Question? Well, because no matter how big this number is in the denominator, when you divide 1 by that, it's always going to be something other than 0. You're always going to have a little bit. Y never equals 0 in this particular problem. Yeah. Now you will have rational functions that'll cross the x-axis, in which case you will have places where it equals 0. But, it doesn't hurt me to tell you now, your rational function r of x equals 0 when the numerator equals 0. But since 1 can't equal 0, you're not going to have a place where it crosses the y-axis or the x-axis. Let's try problem number 16. And let's see if we can't figure out how this graph is going to be changed compared to the graph of y equals x, 1 over x. So in 16, s of x is negative 2 over x plus 2. Excuse me, x minus 2. So there's a couple things that have happened to this graph. And let's focus on the horizontal shift first. What is that x minus 2 in the denominator going to do to the graph? How is it going to shift? Good. It's going to shift to the right by 2. So shifted right by 2. Now the 2 in the numerator is going to provide a stretch. I'm not going to worry about that part of it so much. But how about the negative? What's the negative going to do? It's going to flip it. So it's going to flip. So it's going to flip it. And let's see those changes as we graph them on Desmos. So let's start out with the graph of y equals 1 over x. Y equals 1 over x. That's kind of like our basis for comparison here. And let's zoom in a little bit to there. And then we'll take a look at the graph of y equals 1 over x minus 2. Now that caused the shift that we expected. It caused a shift to the right by 2. So this vertical asymptote is at x equals 2, not at x equals 0. Then the last thing we're going to do is we're going to flip it. Y equals negative of 1 divided by x minus 2. And I understand that there's a 2 in our numerator for the original problem. But what I want you to see is that negative just flips the graph. So if you reflect this graph around the x-axis, then what we had a minute ago is now above the x-axis to the left of 2 and below it to the right of 2. To give you an appreciation for what that negative 2 is going to do in the numerator, let me go a little further. That negative 2 is just going to stretch the graph a little bit. So let me make that a 2. So it just pulls it away from the x-axis. It's tough to envision and appreciate those. What I want you to be able to find is exactly what we did find, and that is, first of all, the vertical asymptote, which is right here at x equals 2. So x equals 2 is your vertical asymptote. Do I have a horizontal asymptote for this graph? Does this graph kind of settle down and approach some number? Yeah. So y equals 0 is your horizontal asymptote. And I'll give you, in fact, I've already given you a handout that discusses some of that, but we'll go over that in a little bit and learn how to just be able to visualize what these asymptotes are going to be. So, two asymptotes in this one. X equals 0 and x equals 2 and y equals 0. Problem 16, they ask you for the domain and the range. So let's cut back to this. What's the domain here? Good. X is not equal to 2. And the range is still y not equal to 0. The graph just never touches that value. Let's try problem number 18. So r of x is 3x minus 3 over x plus 2. This one's a little bit hard to envision what's happening in terms of the horizontal and vertical shifts until we do a little extra work here. If the degree of the numerator is greater than or equal to the degree in the denominator, I'd suggest we do some division. This is going to be the shortest synthetic division problem you'll do. So let's do this synthetically. What number am I going to put out in front here? Negative 2. And then here I'll have a 3 and a negative 3. And oh, by the way, that's going to be my remainder right here. So add going down, I get a 3. Multiply to go up, I get negative 6. Add to go down, I get negative 9. What does that tell me about my polynomial? How could I rewrite this?
X plus 2.
Well, this is my quotient plus, go ahead. Negative 9 over x plus 2. Or you could write it as 3 minus negative 9 over x plus, or 3 minus 9 over x plus 2. But it's a little easier to see what's going on when I write it like this. in terms of its shifting. Let's see if we can't figure out how this has been shifted compared to y equals 1 over x. There's 3 things that I'd want you to notice. Let's start with the easiest part. To the left by 2, right? Because that's your new vertical asymptote. So left by 2. What do you suppose this is going to do? Yeah, it's going to be shifted up by 3. What's the negative going to do? Flip it. Good, it's going to flip it. And finally, the 9 is going to stretch it. I'm not going to worry about that feature of the graph. It is going to be stretched a little bit away from the x-axis. But let's see the effect on the graph here. And we'll kind of do it in pieces. We'll do them one at a time. So let's clear out a few old ones. So do y equals 1 over x plus 2. Oops. Y equals 1 over x plus 2. So that's just going to shift our graph to the left by 2. All right. And then what else can we do? We can do y equals 1 over x plus 2 plus 3. Now that created a vertical shift. Now that's going to change things up a little bit for us. If you start thinking about our range, instead of y not equal to 0, what value of y is this graph not going to pass through? Actually, positive 3. So y equals 3 is going to be a little bit of an issue here. And last but not least, let's flip that upside down. Negative 1 over x plus 2 plus 3. So there's the last of those shifts. Let me get rid of a couple of these other graphs. Just shut those off. Try and write down from this the domain and the range. All right, so John, what's the domain, please?
X cannot equal -2.
Good. X can't equal 2. And Keegan, how about the range, please?
3.
Yeah, so y can't equal 3. All right. Well, let's take a look at the graph here. Let's take a look at the graph. It comes close to this line. Now that line, let me do it this way. Let's look back at this graph. Now the line that it got close to before I shifted it vertically was y equals 0, right? But then when I put the plus 3 in, it shifts the whole graph up by 3. So what was happening at y equals 0 also gets shifted up to by 3. So y equals 3, let's put that in. Y equals 3 is a horizontal asymptote. And you're kind of starting to beg the questions like, well, how am I going to, predict where these horizontal and vertical asymptotes occur? And that's a great question, and we'll go over that next. But in this case, you can see the line y equals 3 is kind of this line the graph will never quite touch. It comes close to, but never quite touches. So it's not part of the range. Any other questions? All right, so how do I predict this stuff in general? I mean, it seems like it's driving me crazy. And if you look at the back of your handout from earlier, I've got it summarized for you. All right, so as far as your vertical asymptotes is concerned, I think we're pretty good at that. Your vertical asymptotes are going to occur where the denominator is 0. So if you're regarding your polynomial as p of x over q of x, as your rational polynomial, then where q of x equals 0, that's where we're going to have a vertical asymptote. Now if q of x can't equal 0, you're not going to have a vertical asymptote. That's fine. For your other asymptotes, there's 3 different cases. Now the first case is if the degree of the denominator is bigger than the degree of the numerator. In that case, y equals 0 is going to be your horizontal asymptote. Now the next case is if the two are equal to each other. So if the degree of the numerator equals the degree of the denominator, then you're going to get this line here. Y equals a over b. Now what are a and b? A and b are the leading coefficients of these polynomials. A is the leading coefficient of p in your numerator, and b is a leading coefficient of q in the denominator. Let's look back at our last problem. Which one of the cases here applies to problem number 18? Yeah, case B. The degree of the numerator equals the degree of the denominator. So let's see what other predictions that makes. It should tell me then that the horizontal asymptote comes from the ratio of these leading coefficients. So it's going to be y. What's the leading coefficient in the numerator? 3. And in the denominator? 1. 3 over 1 gives me 3. That was exactly my horizontal asymptote, was y equals 3. Now there's another case, but we're not going to get there yet. It's called an oblique or slant asymptote. We'll get there in a little bit. For now, let's keep exploring and working with some of these graphs. I think it was your question earlier. You're asking about, well, where do we know where it crosses the axis, right? The x-axis. And a polynomial, a rational polynomial, is going to cross the x-axis where the numerator equals 0. So let's look at problem number 22. It says find the x and y intercepts of the function. So 22 is s of x equals 3x over x minus 5. So if I want to find the x-intercepts, I'm going to set the numerator equal to 0 and solve, set 3x equals 0 to find the x-intercepts. I said x-intercepts in plural. In actuality, how many places is this graph going to cross the x-axis? Where does 3x equal 0? 0. Just divide both sides by 3. Ironically, so to find the x-intercepts, set the numerator equals 0. To find the y-intercept, how do you find the y-intercept of a graph? Yeah, plug in 0 for x. So set x equals 0 to find the y-intercept. But guess what? X equals 0 is also going to be your x and y-intercept. If you set y equals 0, you'll get s of 0 is going to be 0. So this graph should pass through the origin. You'll get 0 over negative 5, which is 0. So if you were to take the time to graph that, it would pass through the origin. You'll have a point right there. 0, 0. Let's try another one. Problem number 26. And at least this one I think will work out with different values. So r of x is x cubed plus 8 over x squared plus 4. So there's two different types of points I want to find. I want to find the x-intercepts, and I want to find the y-intercepts. Let's start with the easy part first, the y-intercepts. To find the y-intercepts, you set x equal to 0. So what's going to happen when x equals 0? What would I get for the y-coordinate? 2. Good. R of 0 would be 8 over 4, which is 2. So 0, 2. Nice. Now comes the tough part. I want to find the x-intercepts, so I'm going to set the numerator equal to 0. So it's x cubed plus 8 equals 0. I'm not worried about the complex roots here. So I could find the complex roots by factoring, but you know what? All I'm interested in is the real root. So let me move the move the 8 to the other side and take the cube root on both sides. What's the cube root of negative 8? Negative 2. Good. So when y is 0, x is negative 2. So there's your intercepts. By the way, if you wanted to factor and solve this, it would be factored as x plus 2 times x squared minus 2x plus 4 equals 0. There's your real root at negative 2. This part is going to have two complex roots. So we don't need to worry about those. That's it. There's your x and y intercepts. You should be able to confirm that with the graph. Let's take a look at that. Let's kill out a few of these. So y equals x to the third plus 8 over x squared plus 4. By the way, can x squared plus 4 ever equal 0? No. And because that's true, I'm not going to get any vertical asymptotes for this graph. So there's your graph. Yay. And we got a root here at negative 2 and 0. Another one, or excuse me, yeah, root at negative 2 and 0, and a y-intercept at 0 and 2. So exactly what we predicted. So far there's two things that you should be picking up. Finding domain and range, and finding your intercepts. We also, guess, we worked with the asymptotes a little bit as well. Let's keep going. Let's take a look at problem number 32. R of x equals 2x minus 3 over x squared minus 1. It says find all horizontal and vertical asymptotes, if any. Well, let's start with the vertical asymptotes, because that's going to be the easier part. Vertical asymptotes are going to occur where the denominator equals 0. How does this factor in the denominator? X plus 1, x minus 1. Where am I going to see horizontal, or where am I going to see vertical asymptotes here? plus or minus 1. Thank you. So vertical asymptotes. Now please do me a favor. Be careful when I ask you where the vertical asymptotes occur. Give me an equation, not just a number. I don't want just 1 and negative 1. Because it makes a difference if you put x equal 1 or y equal 1. They're completely different graphs. So please, I'll try and be careful and remind you to give me an equation, but this is what I want when I'm asking for the vertical asymptotes. Please don't just give me a 1 or negative 1. You might lose some credit. How about the horizontal? Horizontal asymptotes. What case am I dealing with here? Case C or case A? They're not equal, so the degree of the numerator is less than the degree of the denominator. So that'd be case A. What's that telling me then about my horizontal asymptote? Yeah, it's just y equals 0. Eventually this graph is going to come down to the x-axis. So horizontal asymptote is simply y equals 0. Sure. Let's take a look at the degree in both the numerator and denominator. What exponent's understood to be up here? A 1. And down here is a 2. So the degree of the denominator is 2, the degree of the numerator is 1. Since the degree of the denominator is bigger than the degree of the numerator, that's this. The degree of the denominator is bigger than the degree of the numerator, then y equals 0 is your horizontal asymptote. Let's see that when we look at the graph. So y equals, let's just do it again, 2x minus 3. Highlight this, then hit the division key, divided by x squared minus 1. And well, this pretty much has everything we expected, right? So it's getting close to, but not quite touching, the x-axis. We weren't asked for it, but it's giving us the x-intercept. And we can see the vertical asymptotes as well. In fact, we can put those in. We can put in x equal 1 and x equal negative 1. So there's your two vertical asymptotes. The graph approaches very nicely. One thing that people get a little bit nervous about, our graph actually does cross its horizontal asymptote. That's okay. I mean, sometimes they can cross it, particularly when you're dealing with asymptotes that run on a slant. But once it crosses it, I think it's going to stay here. It's going to stay above the x-axis. If you move out the x-axis, it never crosses it again. But it gets really, really close. How would I find the x-intercept for this graph if I wanted to? What would I be doing? Yeah. So 2x minus 3 equals 0, 2x equals 3, x equals 3 halves, or 1.5. So that's the x-intercept, kind of like you saw. And looking good on that one. Let's try some more here. Let's try problem number 36. Give you a chance for one. Maybe I'll help you out a little bit with the denominator. So problem 36. S of x is 8x squared plus 1 divided by 4x squared plus 2x minus 6. Again, you're asked for the same two conclusions. You're asked to try and find the vertical asymptotes and the horizontal asymptotes, or it's typically going to be 1. So the big thing we need to do is we need to figure out if and how this factors. Personally, I think I'd factor out a 2, which leaves behind 2x squared plus x minus 3. And then see if it factors from there. So I'll need a 2 and an x. And let's think. We'll do a plus 3 and a minus 1. Is that going to work? Lucas, you're the master on this one. Let's see. Yeah, that works. Okay, so there's a little bit of a head start for you. See if you can't figure out vertical asymptotes and the horizontal asymptote. So in the denominator, depends how good you are. You can read some of these off. Certainly, I hope you can read off x equal 1 is going to be a vertical asymptote. Now, the 2 doesn't really matter here. What matters is where 2x plus 3 equals 0, which is going to be 2x equal negative 3 or x equal negative 3 halves. So x equal negative 3 halves is where you're going to have your other vertical asymptote. How about your horizontal asymptote? What case are we dealing with from our horizontal asymptote list? Case B, where these two things are equal. So the degree of the numerator is 2, the degree of the denominator is 2. You're going to get y equals 8 over 4, which is 2. So that's your horizontal asymptote. No, because if you put in a 0 here, let's go over to here. If I put in a 0, I'd get negative 6 in the denominator. So putting in a 0 doesn't create a place where the denominator is 0. 2 can't equal 0. Yeah, if there was an x there, then yeah, you'd be exactly right. Let's look at problem number 44. Kind of going back to a slightly simpler problem. R of x is 2x over x plus 6, or excuse me, 2x plus 6 over negative 6x plus 3. Let's bang out a couple of quick asymptotes here. Let's start with the horizontal asymptote. Thank you. Y equals 2 over negative 6, which is negative 1/3. Yay. How about the vertical asymptote? Got to be a little more careful. I mean, you're doing the right thing. You just made a little. Negative 6x plus 3 equals 0. So it's going to be 3 equals 6x. 3 divided by 6 is 1/2. So, nice. Can anyone tell me where this graph actually crosses the x-axis? Where would it cross the x-axis? Yeah, 2x plus 6 equals 0 means x equals negative 3. All right, let's graph that. Oh, wait, that's been done for you. So, I'll probably not give you fractional asymptotes because they're kind of a pain to graph. But here's our asymptotes. We've got a vertical one at x equals 1/2. We've got a horizontal one at y equals negative 1/3. And along the way, we picked up our x-intercept at negative 3. So, nice. When you graph these things, start with the vertical and horizontal asymptotes. They really frame your graph. Are you getting the gist of these rational functions? Let's do a couple more. Let's try problem number 54. So r of x equals 2x squared plus 10x minus 12 divided by x squared plus x minus 6. There's a lot of information we can find from this graph. Let's see what we can do. We'll start with the horizontal asymptote. What's that going to equal? Yeah, these two match. So 2 divided by 1 is 2. If you just write y equals 2, I'll be very happy. Let's take a look at the vertical asymptotes. Basically for that, I got to know where x squared plus x minus 6 equals 0. I hope you're not pulling out the quadratic formula for that one. The vertical asymptotes are going to be at negative 3 and 2. Now let's find one other, maybe two other things for this graph. You're asked to find the x and y intercepts. We'll start with the easy part, the y-intercept. To find the y-intercept, you set x equals 0. So if I set x equal to 0, this is 0, this is 0, I end up with r of 0 is negative 12 over 6. Just give me negative 6. So positive 2 for my intercept. Okay. How about flipping things around? If I want to find the x-intercepts, I'm going to set y equals 0. Basically, it's setting the numerator equals 0. So it's going to be 2x squared plus 10x minus 12. I'd factor out the 2 first. Once you factor out the 2, then you're in good shape. This will factor as x plus 6, x minus 1, and I get 2 intercepts. Let me keep a little t-table, kind of a running scorecard of our points. When I set x equals 0, I got y was 2. If I set y equals 0, I get 2 possibilities, negative 6 and 1 respectively. As far as graphing these are concerned, I've given you a little bit of a head start here. Here's x equal 2. Here's x equal negative 3. Here's y equals 2. No, is that y equals 2? Was it? Yeah, y equals 2. Let's also put in a couple other points, some important points. So 0 and 2, that's going to be on our graph. That's going to be right here. Negative 6 and 0. Yeah, about there. And 1 and 0. As far as the rest of it's concerned, boy, there's a lot of stuff that we haven't really filled in yet. But near an asymptote, the behavior of your function is going to be one of two things. Either it's going to go up towards positive infinity or down towards negative infinity. And the same thing with the other side of the asymptote. So what do you suppose I'm going to do to figure out what the rest of this looks like? Yeah, graph it. I'm not going to take away your graphing calculators for the test. All right, I encourage you to use them. Let's take a look at what this graph's going to be. Let me get rid of a few of these other graphs. So y equals 2x squared plus 10x minus 12. I don't want the s there. And that's going to get divided by x squared plus x minus 6. Did I type that in quite right? Oh, thank you. 2. Yeah, yeah, I had an S by accident. There we go. Because I was looking at there going, wait a minute, it doesn't have the right x-intercept. There we go. Nailed it. So for the rest of it, we can just kind of copy the graph from our graphing calculator or from Desmos or whatever. But the important features are there. The things that I wanted you to find were the intercepts and the asymptotes. So just draw a reasonable sketch from here. I'm not going to ask that you give up your graphing calculators. Let me just take one look back at the graph here. Yeah, okay. So something like this, this, and then was the other one above? Yeah, okay, so something like this. I'm not really interested in you plotting lots of points. The only points that I'm really going to be anxious to see you give me are the x and y intercepts. And that's it. The rest of it, kind of pick it up from the graph. Not that you should blow off practicing these things thinking, oh, gee, you know, I don't need to practice these things because I have a graphing calculator. Some of these problems, the graphs look pretty messy just because of the nature of your graphing calculator, especially some of your older ones. Sometimes when it graphs it, it looks like it's trying to draw a vertical asymptote for you. In fact, on your 83, if you were to look at that, you probably, depending on how you graph it, you'll probably see it try and connect the dots between these things. And it'll look like it draws your vertical asymptote there. It's not really doing that. Okay, so let's do one or two more for this section, and we'll call it a day. I'm not going to get to section 3.7 today. I know you're really sad about that. Don't worry, I'll make it up to you. So if you're looking at our cases here, you've noticed that we've left one out. What haven't we done yet?
The slant.
Yeah, the slant asymptote. So this case is exactly when the numerator is 1 degree bigger than the denominator. So if I have a degree 2 polynomial in the numerator, I'll have a degree 1 polynomial in the denominator, or 3 and 2, etc. The degree of the numerator is 1 bigger than the degree of the denominator. So that's what I'm talking about for a problem like number 70. Let's check that one out. So problem 70 looks like this. X squared plus 2x over x minus 1. Now to understand and figure out what that slant asymptote is, and notice the degree of the numerator is 1 bigger than the degree of the denominator, what you need to do is you need to divide things. So you're going to come up with the quotient and the remainder. And it's going to be this quotient that's going to give you the equation of your slant asymptote. So I need to divide x squared plus 2x by x minus 1. So you could do it longhand, but a lot of you probably aren't really all that great at doing it by longhand. So what's another way I can do this division? Synthetic division. 1, 2, and 0. So run through the synthetic division and see if you can't tell me what you get for r of x here. Or I mean that quotient, I should say. Quotient remainder. Well, let's see. I haven't called on Kenny in a while. Where am I going to start? Thank you, sir. All right. So 1 times 1 is 1. Add, we get a 3, 3, and 3. Great. But what's that tell me? What can I do here? What should I write? Good. This is your constant term. That's your term in x. So this is x plus 3 over x minus 1. In particular, that x plus 3 was what's called your quotient. And that x plus 3 is your horizontal, your oblique asymptote. So y equals x plus 3 is the oblique or slant asymptote. The reason for that, the reason we're getting such strange behavior like that can be kind of, divined if you think about what's going to happen if I put in really, really big values of x to this. Values like 1,000,001 or 1,000,000,001, 1,000,000,001. What happens to this ratio? Is it going to be very big?
Tiny.
It's going to be really, really tiny. So it's going to start, after a while, it's not going to make a really meaningful contribution. It's just going to kind of disappear. So overall, the behavior of the graph starts to look just like this because the contribution from this gets negligible and it won't make a big difference. So that's why you get this kind of behavior. Now, even though we have a oblique asymptote here, we still have a vertical asymptote. Question, yeah.
Where did you get the 3 and the 3 over x minus 1?
So this right here is your remainder. That's your coefficient of the constant. That's your coefficient of x. So 1x plus 3, remainder over x minus 1. How about our vertical asymptote? Where's our vertical asymptote on this one? You can go back here or here. Paige, where's the vertical asymptote on this one?
Do I do the top part?
I don't know. How do we find the vertical asymptote? X equal 1. Yes. It's where the denominator equals 0. So where the denominator equals 0, x equal 1, that's your vertical asymptote. And then you can graph it. All right. Now, I've already kind of helped you out here. I've got your oblique asymptote, that's y equals x plus 3. I've got your vertical asymptote, that's x equal 1. And then you can look at your graphing calculator for the rest. Very helpfully, I put in a couple points here for you on your graph to kind of help guide you. Those are the minimums and maximums, but I'm not going to ask that you find those. What I'm looking for roughly is this shape. Okay? So that approaches the asymptotes from the correct side. I looked at the graph. You can use calculus too if you wanted to cheat, but it's just not. These are not points that I would ask you to determine. That is above and beyond this class. All I want is the correct general shape wedged in between the asymptotes there, the vertical and the slant asymptote. Well, any predictions as to what problem we want to do last? 72? All right, let's do 72, especially since it's already somewhat done for us. So for problem 72, we've got r of x is, where is it? 3x minus x squared divided by 2x minus 2. Now, you need to be a little bit careful in this one if you're going to do it by synthetic division. There's really two things that are going to kind of mess us up. The first is that the numerator is in the wrong order. The second is that the denominator isn't just x minus something or x plus something. You've got that factor of a 2 here. So I'm going to factor that 2 out. Factor out that 2, it leaves behind x minus 1. In fact, I'm going to factor that all the way out. Just write it as 1/2 times negative x squared plus 3x over x minus 1. And now we can work with this by synthetic division. The important thing I want you to see is you can't work with it by synthetic division here because you've got something in front of the x. You can't have anything in front of the x there. So, what number goes in front here? All right, a 1 goes in front. We're not worried about the 1/2 right now. We're just worried about this part right here in those manly pink parentheses. Let's, I said that with a straight face. -1 plus 3 and 0. Add, multiply, add, multiply, add. So what can I replace that with? Nice. Now, I won't give you one this tricky on an exam. I'm not going to make you factor out the 1/2. But if you did follow through this one, then let's distribute the 1/2 and get negative 1/2 x plus 1. 2 times 1/2 is going to cancel. But this quotient, as before, that's my slant asymptote. Right there, negative 1/2 x plus 1. Okay, let's see. Yeah, you can kind of see that here. Here's your y-intercept at 1. This point is at 2. So this is your equation, y equals negative 1/2 x plus 1. I think there's a vertical asymptote here at x equal 1. It's not drawn in, but you can figure out that by just looking at the graph. And I think I have that one graphed. Yeah, down here. So there's your graph. So it's going to look kind of like this. Here, and then like that as well. And I think I accidentally crossed over a vertical asymptote, but that's all right. Let me give you some homework and get us out of here. For homework, try 11 through 55 and 69 through 73. So those last handful are your slant asymptotes. That's 3.6, yes. All right, there's a test on Thursday. So